For those of you who don't know me, I am Matt Lalonde, also known as the guy that Rob Wolf simply won't shut up about. I have a PhD in organic chemistry from Harvard University, so I guess legally my name is Dr. Matthew Lalonde, but I am not, and I'm stressing this, I am not a physician, and I'm not a dietitian, nor am I an MD. So by law, that means that I'm not allowed to give advice. I'm not allowed to tell people what to eat. Hence, the disclaimer that you see here. So this is at the beginning of every slideshow. I'm just going to read it once. So this seminar is given with the understanding that the lecturer is not rendering medical advice of any kind. The information in these notes and lectures is not intended to replace medical advice, have not been evaluated by the Food and Drug Administration or whatever its equivalent is in Canada, and are not intended to diagnose, treat, cure, or prevent any disease. Full medical clearance from a licensed physician should be obtained before beginning any diet. The information and opinions expressed in this lecture and these slide notes are intended for educational purposes only. The lecturer claims no responsibility to any person or entity for any liability, loss, or damage caused or alleged to be caused directly or indirectly as a result of the use, application, or interpretation of this material therein. And I had a Harvard lawyer put that together for me. So you can tell the type of language. Before we start, I'd just like to get a feeling for how many of you are box owners or trainers. I'd like to raise your hands. All right, like a little less than 50%. And then the rest of you are athletes, I imagine. Is that correct? So how many of you are like CrossFitting athletes? Raise your hands. Okay. So the rest of you people, you just want to look good naked, is what Rob Wolf would say? All right. How many of you have had like some kind of, dare I say, college-level science class? Okay. Did I mention I was? This is gonna hurt. Danny, you might want to bring out the pukey buckets. As Rob Wolf likes to say, people's heads are going to be spinning exorcist style. The reason I decided to do this is because I was not necessarily satisfied with the approach that had been taken with others. Not to say that what they were doing isn't legit. I just think that there's a lot of very legitimate science to be presented with respect to this diet and this way of eating, and that the current way in which it is addressed is just lends itself very easily to being discredited. So I'm going to present a heck of a lot of science, probably more than you're going to be comfortable with. So people are going to be leaving here, and I've had like someone walk out of my seminar like this, and I'm like, dude, did you throw out your back? He's like, no, I just feel like if I tilt my head, there's information that's going to leak out of my ears. But if you understand about 10% of what's on the slides, I'll be happy. Everything that you see here is going to be sent to you. Make sure we have your email address. It's going to be sent to you via email, so you don't need to like frantically take notes. But if I say something that's not necessarily on the slide, then feel free to write it down. The reason why I choose to do it that way is that even if you don't get all of the material, you at least have something to fall back on if you're trying to explain your lifestyle to someone else. And if you want to educate yourself further in the future, you're going to have a few key words like, maybe I should look up AMPK and its effect on SIRT1 and, the AMP and stuff like that. So I think that it's really important for folks to have that, and it's just like in one nice package. I will start with like a basic intro to make sure that everybody's on the same page. So some of this stuff might be review, some of you. It might be completely new to others, and that's totally fine. So without further ado, let's get started. There's a lot of material to cover, so I like to get started as soon as possible. So carbohydrates, if you were to ask a chemist, gee, what's a carbohydrate? I'm a chemist, not a biochemist, I'm an organic chemist. There's a slight difference there. The scientific definition is like any molecule that it will fill in this formula, and you can tell, for example, glucose is, C6H6O6, C6H12O6, sorry. So for those of you, H12O6. So if I were to divide every number here by 2, I would get something that's like CH2O, right? And if I put this in parentheses, you see the C stands for the element carbon, H2O water, so we say carbohydrate. This is an old school definition. It turns out that it doesn't hold anymore. There's carbohydrates that have nitrogen atoms in them and whatnot. It doesn't really matter. The carbohydrates are what we know as sugars, right? They're synonymous with saccharides as well, and they're divided in about 4 categories. You got your monosaccharides, your disaccharides, oligosaccharides, and polysaccharides. Things like glucose, sucrose, starch are really good examples of that. Agave nectar is about 90 to 92% fructose, and fructose is a monosaccharide. So the monosaccharide is our basic building unit. You know, if you're building a house, it's your brick. It's that one brick. I also like to use the analogy, although most people don't get that anymore. You know, anybody play with monkeys in a barrel when they were a kid? Yeah, that used to be fun. It got old pretty quickly. But imagine that every monkey is a monosaccharide. It's a chain of them, and that chain is your polysaccharide. So that's another way to think of it. You can also think of them as chain links. They're just basic building units. Legos, they'll do too. So your basic building units, there are various types, various flavors. I think everybody's heard of glucose. That's also referred to as dextrose. And there's fructose. That has a couple of other names. Galactose, xylose, ribose. These are all carbohydrates. And notice the ending in OSE, O's. So from now on, you hear something that, glucose, fructose, that should ring a bell. That's like carbohydrate. You have disaccharides. Sucrose is table sugar, and table sugar is one molecule of glucose and one molecule of fructose bound together. So we say disaccharide because there's 2, and they're just linked together, kind of like the monkeys in the barrel, right? You got 2 monkeys. Lactose is another one. That's glucose plus galactose, and then maltose is just 2 molecules of glucose stuck together. And here's our favorite disaccharide, everybody's pure white crack, which is table sugar. Oligosaccharides, so that's anything that's like 3 or more monosaccharides, right? So 3 monkeys in the barrel stuck together. Anything that's like 3 or 9 is referred to as an oligosaccharide, and then anything that's above 10 is a polysaccharide. There's people that argue about the differences there. It's like, no, I think that it should be this number that's an oligosaccharide, this number that's a polysaccharide. It really doesn't matter. But the ones that are important here are things like starch. I think everybody's heard of that, so that's a polysaccharide. Glycogen, right? This is how our muscles and the liver store carbohydrates. So that's another polysaccharide. And then fiber, of course, whether it's soluble or insoluble. That's a polysaccharide. One thing that you should note, anybody here of essential and non-essential nutrients? All right, raise your hand. You've heard of essential. What's the difference? Why is something essential? Body can't make it on its own, right? And something that's not essential, the body can make it. There is no essential carbohydrate. Keep that in mind. There's absolutely no essential carbohydrate. The body needs glucose to survive. Specifically, the brain needs glucose to survive. It does not run exclusively on glucose. That's a myth. It can run on a mixture that's about 75% ketone bodies, 25% glucose at the maximum. But it does need glucose to survive. The reason why glucose is not essential is because your body can make it. It can make it from glycerol, which is the backbone of triglycerides, which are fats, and it can make it from protein and various amino acids. So amino acids are the building blocks of protein. So very much like the monosaccharides. They're your monkeys in your barrel. They're your Legos. They're the things that you link together to make longer chains. There's about 21 amino acids, if you include the selenium-containing one, that are found in eukaryotes. That's our cells. And then they're separated into various categories. You have essential and non-essential, and you have glucogenic and non-glucogenic. The glucogenic amino acids can be turned into sugar. The non-glucogenic amino acids cannot. Right? So that's the only difference here. So the essential ones, you essentially have isoleucine, leucine, lysine, methionine, phenylalanine, threonine, tryptophan, and valine. And then the non-essential ones are essentially all of these other ones. You're going to see a lot of endings in INE with a few exceptions like tryptophan and so on and so on. So when you see that, you think, okay, that's probably an amino acid that's a building block of a protein. Right? That's a good gauge. So the combination of your essential and non-essential gives you all 21 amino acids. The combination of glucogenic and non-glucogenic doesn't necessarily give you all 21, and that's because they can't all be turned into sugar. So The glucogenic amino acids are glycine, serine, valine, and so on. A lot of the details that are on the slides I essentially put there because when you look through those later on, at least I'm hoping some people are going to look through them after the seminar, you'll remember what this long-winded scientist was saying, right? So what the heck was he talking about again? Okay, it's over here. So there's a lot of this bullet point stuff that I'm going to skip over as the seminar goes along. It's just because I've memorized this stuff. Right, so if you look at this, I've already mentioned this, already mentioned that. So here's this monkeys in the barrel, my favorite game when I was a kid. It didn't take much to entertain me. So proteins are polymers of amino acids, so a lot of amino acids stuck together. And then enzymes are proteins. The only caveat is that they catalyze chemical reactions. And when I say that, like, people, whoa, what the heck are you talking about? Imagine that you've got an assembly line, people making a car, making something. Every person that is along that assembly line you can think of as an enzyme. They have a purpose. They're taking a starting material and they're transforming it to a product. So those are the enzymes, and most of them are proteins. So they're going to become increasingly important. So when you guys see enzyme, I just want you to think of a worker, someone who's doing something, who's doing a transformation. Okay, that's for those of you who don't have like the biology background. I think that's a really interesting way of seeing it. I try to be as accurate and complete as possible. I do have to skip certain details. Otherwise, this would be transformed into a semester-long level course in like endocrinology, biochemistry, and organic chemistry. And obviously, we can't do that in one day. So the next building blocks, the lipids, right? We have saturated, so laureate, myristate, palmitate, stearate. You're also going to see lauric acid, palmitic acid. These are the same thing. The only difference is that the laureate, the term ate, refers to the negatively charged version. So for those of you who know, the fatty acids are essentially carboxylic acids that have a long fatty acid carbon chain, and if that carboxylic acid is deprotonated, then we'll say that it's laureate. If it's protonated, we'll say it's lauric acid. Those are details for those of you that are biochemists. If you hear laureate or lauric acid, it's the same darn thing, right, as far as our purposes are concerned. So we have trans fatty acids. I think most people have heard of trans fatty acids, right? They're bad. We're taught to think that they're really, really bad. The synthetic ones are bad. But it turns out that there's naturally occurring ones. And the naturally occurring ones are really, really good. So you have things like vaccinic acid and conjugated linoleic acid. I'm going to talk a bit more about this stuff. Conjugated linoleic acid, I think, is one of the most potent anti-cancer compounds that is known. And what's really frustrating, and it was just a matter of time before this happened, there's a recent article that came out. The research was sponsored by the Beef Council, of course, that said that the corn-fed meat was better than the grass-fed meat. And they're saying, oh yeah, it's better than the grass-fed meat because it increases HDL more. We'll see why that's the case. And also, this grass-fed stuff has more trans fats in it, and it's bad. And they're just trying to use the people's ignorance to their advantage and trying to convince people that this is a bad thing. It's actually a good thing because the trans fats, the naturally occurring trans fats that are in that meat are vaccinic acid and conjugated linoleic acid. Just, school yourself on the matter, Google through this stuff, and you'll see for yourself. I'm not saying that, Google or Wikipedia is like the ultimate source of information in the world, but it's a start. So, monounsaturated fat, there's plenty of these, but the one that is most relevant is oleic acid or oleate. And then we have the polyunsaturates, which we're going to talk about quite a bit, the omega-6, so you have linoleic acid, arachidonic acid, and a bunch of stuff in between. We'll go through that quickly. And then omega-3s, which are alpha-linoleic acid, eicosapentaenoic acid, docosahexaenoic acid, and a variety of others. We'll have a slide about all the intermediates, or most of the intermediates, later on in the talk. For those of you who really have to know what are the numbers, the 12 stands for the number of carbon atoms in the chain of the fatty acid. 0 stands for the number of unsaturation. So this is fully saturated. There are no unsaturations, so this is 0. This is monounsaturated, so this is 1. This N9 refers to the position of the double bond along the chain. If you're listening to this and it's like, this sounds like English, but I have no clue what the heck he's saying, don't worry about it. There's a few people that are going to understand that. That's fine. If you don't understand that, it's not necessary. So like I said, if you get like 10% of what I'm saying, I'll be happy. It's not going to change the prescription at the end of the day, but it will hopefully allow you to educate yourself a little further on. Cholesterol, this is supposedly bad. We'll determine that shortly. This is a really important chemical, and I call it a chemical because I'm a chemist. Chemicals aren't necessarily all bad. I make the argument that human beings are just like a big bag of well-organized reactions, and that pisses off a lot of people, especially religious ones. This is a chemical that serves as a starting material for many essential biomolecules. So it is the starting material to make all steroid hormones, whether it's progestins, glucocorticoids, mineralocorticoids, androgens, estrogens. Also the starting material for bile acids and bile salts, and we're going to see shortly why this is important and what the action of these things is. They also repair and maintenance of cell walls. Cholesterol is really important for that. And vitamin D synthesis, obviously. So you look at that, it's like, wow, this looks really important. I wonder why people are making a huge fuss over it. They're needlessly making a huge fuss over it, and we're going to cover that. This is a really important molecule, and obviously, because of that, its synthesis is pretty tightly regulated. We're going to talk a lot about lipoproteins. HDL, LDL, VLDL, those are probably terms that you've heard before. Is it good? Is it bad? Gee, I don't know. What does it eat during the wintertime? The name implies it's a lipoprotein, and it essentially has phospholipids and apoproteins. So these phospholipids are these little things that you see here. Is anybody familiar with the functioning of soap? Like, how does soap dissolve grease? Anybody know?
I think it surrounds, like, charge, and then the charge surrounds the molecule, and it can carry it away.
Good for you. Good for you. Did everybody hear that? So soap is essentially deprotonate. It's a salt of a fatty acid, and the fatty part interacts with the fat, and the charged part interacts with the water. And the fatty part surrounds the fat and allows the fat to be transported in water. Phospholipids, we call those micelles. Phospholipids are very analogous to that. It's like a little, I like to refer to them as submarines. Human beings can't survive underwater. So what do? Well, we build submarines that have air in them so we can, explore underwater. Well, the same thing happens in fat. Blood is an aqueous environment. We know that oil and water don't mix. So the body uses lipoproteins to transport fats throughout the body. So they're classified by their density, and we're going to cover that very shortly. There's I think about 5 flavors of these chylomicrons, which are the lipoproteins that come straight out of the intestines. I'm not going to read all this. This is for your own knowledge. VLDL stands for very low density lipoprotein. We're going to get into that in some more details shortly. IDL is intermediate density. HDL is high density. Everybody's heard of that, right? Oh boy, this is the good cholesterol. And then LDL is a low density lipoprotein. The whole good cholesterol, bad cholesterol thing is really unfortunate because we're not necessarily talking about cholesterol. What they're doing is measuring the amount of cholesterol that lipoproteins are transporting around, and they're using that as a way to estimate how much lipoprotein you have in your body. So it's confusing because when you say good cholesterol, bad cholesterol, you're actually not talking about the amount of cholesterol. You're talking about an estimate of the lipoprotein content of the blood. This is more details on these things. Hormones and eicosanoids. Who's heard of eicosanoids? Barry Sears loves the eicosanoids. We're going to talk about eicosanoids too a little bit. So what are hormones? Hormones are signaling molecules. They're a way for cells to communicate with one another. And the things that we call hormones typically act long distance. So from a fat cell that's around my waist to my brain, for example. Just an adipokine is going to do that. So things, like insulin, for example, is a hormone. So they're essentially signaling molecules. They tend to act long distance. The eicosanoids are also hormones. There's two specific things about them, however. They're all made from 20 carbon molecules, from 20 carbon fatty acids, polyunsaturated fatty acids. Icosa means 20. So if you're a chemist and you've studied a little bit of nomenclature, you know how to write the names of molecules, the icosa means something to you. So there's a lot of these names that may seem really, really weird to you, but it means something to a chemist that's reading it. And if you can teach some of this stuff, you are going to kick ass at Scrabble. I mean, I once used the term xylol to totally destroy someone at a Scrabble, and then we looked it up in a dictionary, and it was actually there. So I'm a nerd. I just gave myself away. In disguise, most people look at me, it doesn't look that nerdy, so I'm just going, I'm a nerd. Proper intercellular communication is crucial for health and longevity, obviously. So the eicosanoids, not only are they made from those 20-carbon polyunsaturated fatty acids, they're for short-term communication, just in between cell. The eicosanoid is essentially you yelling at your neighbor, right? Whereas the hormone is you like sending an email or a phone call to someone across the world. So the ones that we're going to be concerned with, insulin and glucagon, those words might be familiar to many of you. Leptin and ghrelin, adiponectin, and peptide YY. I'm not going to talk a whole lot about that one because this gets in nitty-gritty. This starts to get into the detail. Cortisol I will definitely mention. Insulin-like growth factor, one, that's typically an important one, human growth hormone as well, and then testosterone, everybody's favorite. A couple of words that are going to come up now and then. Chronic versus acute. So what do I mean by that? So something that is acutely toxic means that like one single large exposure or maybe multiple moderate exposures within a short period of time, right? So think of like you having a huge cheat meal, 3 pints of ice cream. I would say that's acute exposure to fructose. Okay, that essentially sums it up. Chronic toxicity is like continuous and repeated. The dose isn't necessarily high, but it's like constant over a long period of time. For example, someone who's an alcoholic, has 3-4 drinks every day for years, that would be chronic exposure to alcohol. Okay, so that's the difference between acute. Acute, large dose, short term, chronic, moderate to small dose, long term. Also going to hear the words postprandial and fasting. Postprandial is immediately after a meal, whereas fasting is typically after 12 hours of not eating. So if you get a blood test done and you want to get some biomarkers and stuff, that's typically going to be done fasting. But there is some decent information that can be obtained from postprandial results as well. Like if you find that you eat a meal, not necessarily carbohydrate rich, but every time you eat, your blood sugars spike a whole lot, that's telling you something. Postprandially. That's telling you something really important. The scientific method, near and dear to my heart. I need to cover this because we need to know the difference between science and scientific evidence and anecdotal evidence. And then how to determine what's good science and what's bad science. I think this, hopefully when you leave today, my goal is that you are going to understand where all the confusion with respect to nutrition comes from. Right? Why are people confused? Why do I read one day that fat is good and then the next day that fat is bad? And then we have some people from the National Post here, is that right? Yeah? Okay. Your people, the media does a terrible job of covering nutrition, I'm sorry. I mean, it's just a piss poor job and I despise them in that regard. I really wish you guys would get some science education, I'm sorry. I'm sorry. All right. I'm glad you're here, though. Do you cover any nutrition? What was that? That's right. That's right. So, what is the scientific method? Well, first and foremost, you define a question, and then you gather some information. You do a little bit of research, you observe, and then you formulate a hypothesis. Would it be possible that X causes Y, for example? That's my hypothesis. And then you devise and perform experiments to test this hypothesis. As you do that, you collect data, you analyze data, you interpret data, and then you come to a conclusion. Was my hypothesis validated? Yes or no? And then you publish the results and you retest. It is very important for me to stress that the process can go wrong at any of these steps. And just because something was published does not mean that it's correct. I have, my best friend. We are very, very different individuals. He's not a scientist, and he thinks that, to him, scientists should be infallible. When something comes out in the newspaper, it says, scientists discovered this, that has to be right. And I look at it in a completely different way. I'm like, are you delusional? We are dealing with some of the most complicated systems, multivariate, you can imagine, especially when it's a human body and nutrition. Some of us are biased, others are not. Some of us, are better at this process than others. Of course we're going to make mistakes. Absolutely. We're in Toronto right now. David Jenkins, some of you may have heard of him. He's a moral vegan, does nutrition research here in Toronto. If I ask him, what diet do you think is best, what do you think his answer is going to be? He's biased, right? As a chemist, as someone who does not soft science, I don't consider nutritional science to be science. I'm sorry if I insult anybody by saying that. Someone who does real hardcore science, I look at this nutritional field and I'm like, wow, this is the government is funding someone who is obviously biased. If I were to go into research and think that I have the answer from the start, that's a wrong approach, right? I shouldn't be trying to prove myself right. I shouldn't think that I am right. I should be looking for the truth. Scientists are looking for the truth, the good ones anyways, but never necessarily find it. And there's this really good quote by André Gide who says, that you should trust people who are looking for the truth, but beware of those who say they have found it. So you should constantly be looking for the truth. Unfortunately, there are scientists that they take this personally. They just can't admit that, oh man, I screwed up and I was wrong, and they just can't deal with that. And it's unfortunate, and you have a lot of that in the world of science. If, I run a chemical reaction, it's like, oh yeah, that was wrong, but hey, let me try to determine why I was wrong, and there's typically something really interesting lying there. But in the world of nutrition, it seems like people just don't do that enough. They have personal stake in it more so than anything I've ever seen, which is truly unfortunate because the public suffers as a result, and we're going to see that. So this is something that I mentioned a little bit. So the scientific method should be, and this is something that should be familiar to you, observable, measurable, and repeatable. So if I run a scientific experiment and I publish it with something that's called an experimental section. The experimental section will detail exactly what I did to get my results. Someone else can take my paper, read it, and try to reproduce the result. If they get a different result, they say, hey, you screwed up, right? Or, hey, I'm looking at your data interpretation, I think it's wrong. Science is open source and open access, and anybody can come by and say, hey, I'm questioning what you said there. But speaking of questions, by the way, feel free to holler, raise your hand if you have a question throughout. Scientists are pretty darn nasty when it comes to seminar. I'm used to being constantly interrupted by people who know a lot more about the subject than I do. And it's like, hey, what's your evidence for that? How do you know this? And what's the mechanism for that? So, go ahead and interrupt me all you want. This is it's no sweat. So over time, as I've said, scientific information tends to become more accurate. It may never be the truth, but it should get closer and closer to the truth. Anecdotal evidence, much less reliable than scientific information. And that's because anecdotal evidence is typically not recorded in a rigorous fashion. The experimental conditions associated with anecdotal evidence are often unknown, and the experiments themselves lack adequate controls. So anecdotal evidence may itself be true and verifiable, right? Just because it's anecdotal doesn't mean it's wrong, but is often used to deduce a conclusion that does not follow from it, usually by insufficient amount of evidence. So for example, my grandmother smoked like a chimney and died healthy in a car crash at the age of 99. That doesn't mean that smoking markedly increases the probability of cancer and heart disease at a relatively early age, right? It doesn't disprove this fact. We're looking at one person, and what I really would want to know, or what I really need, is a clone of this person who lived the same life without smoking, and then I could compare the two accurately. Then that would be anecdote. That would be more legitimate scientific evidence. This doesn't tell me anything. Now we get into epidemiological studies. And we need to get into that because they're slightly different from scientific studies, and there's a lot of this stuff in nutrition. So as the name implies, whether it's observational, prospective, cohort, or epidemiological, they're not exactly the same, but they share very similar aspects and characteristics. As the name implies, this evolved from the study of epidemiology, so infectious diseases. You have a bunch of people, they're all sick, and you have them fill out a survey. I'm like, I want to know what you ate, I want to know where you were, what water you drank, what places you visited, etc. And then they look at the variables and they see, everybody who got sick drank water from this well. That must be the cause of the disease, right? So everybody understands when you have an infectious disease, that works very well. But over the years, this stuff is being increasingly applied to things like obesity and heart disease, diseases that are non-infectious in nature. There's always someone when I say that, it's like, oh yeah, but there's this recent report that came out that says obesity is infectious. I'm like, no, listen. They looked at people who were obese, and they determined that if you were hanging out with people who were really overweight, then your chance of picking up their bad habits was pretty good, and that meant that you were probably going to be overweight eventually too. That's not necessarily like direct, infection. That is a very different process. So you can imagine these things like heart disease, diabetes, and whatnot. These are multivariate problems. So is epidemiology from a certain standpoint. But you cannot say at the end of the day, when you're looking at non-infectious diseases, that because you see a correlation between X and Y, X must cause Y. You can't say that because it's just too complex, right? So I'm not saying that epidemiological studies within the realm of nutrition are useless. They're actually really useful for formulating hypotheses, but they only give you correlation. They do not give you causation. And there's people who say, but if you do Monte Carlo analysis and linear regression analysis and whatnot, you get like a better idea of what's correlated to what. It still doesn't give you causation. When it comes to non-infectious diseases, you need a controlled trial. You absolutely need a controlled trial. But these things are not useless. They tell you what's correlated with what, and that's something to investigate further. Like, maybe I should look at whether or not this causes that there might be something there. Whether or not it makes sense. Sometimes we discover some pretty funky things that we really couldn't imagine were related, but actually are. So this is kind of like a tree of like what's a controlled trial, what's an epidemiological study, and the flavors that come along with that. So just to give you an idea of why you should beware of these things, here's a nice epidemiological study: toothbrushing, inflammation, and risk of cardiovascular disease. And they find that people who brush their teeth more often and don't have inflamed gums have less cardiovascular disease. Do you think that if you increase your rate of toothbrushing, you're going to get fewer risks of heart attacks? No, right? This is a correlation. There's something else, another variable that's not being looked at, something that we call a confounding variable, that explains the result. And if you look at it, the authors admit that, though the causal nature of the association is yet to be determined. Right? So they say, this is just an association, we have to determine the cause, we're not sure yet. But there could be something legitimate here, right? Because this gum disease, this inflammation, could be related to inflammation that's causing heart disease. But this is just a correlation. And here's a more egregious one. Shaving, coronary heart disease, and stroke. Turns out that if you shave more often, your chance of getting a stroke and a coronary heart disease are much lower. Okay. Do you think that's causal? No. Right? That's just a correlation. And if you read the abstract, the authors list a bunch of other variables that could explain what's going on here. It turns out that the people who shaved more often had better jobs, were more educated, they were married, lived in, had better living situations, etc., etc. So you really have to be aware of this thing. But when the media picks up on this stuff, and I some of you who are on my Facebook page, you know that I love to pick up stuff on Science Daily, they're going to be like, ooh, this causes that. And then you click on the link, it's like, no, it's an epidemiological study. Right? So as soon as you see that the stuff is an epidemiological study, you don't necessarily dismiss it, but say, no, it's just correlation. Right? It's not cause and effect. It's just a correlation, and it doesn't mean that X causes Y. So what are control trials? With the control trials, you're trying to isolate the variables. And this is something that chemists and other scientists do fairly typically in the lab to try to get a handle on what's causing what. This is a lot more difficult to do with human beings because obviously you're dealing with a multivariate system that is within a multivariate environment. All right? Really, really complicated stuff. I can't stress that enough. So even control trials can be wrong. You really have to look at the details and nitty-gritty of the stuff, determine whether or not it's right. But a control trial will give you typically a better idea of whether or not you've got cause and effect because they're going to isolate the population. I have two groups. One is my control groups. One is the experimental group. And in one of them, I'm giving them, let's say, more sugar, and the other one I'm giving them less sugar. And I want to see what's the difference between the two over time, right? So you try to control things, but really you have different people who have different genetic makeup and whatnot, so there's still some variability, but you're doing your best to minimize that and get a better idea of what's going on. So that's why control trials are a bit more reliable. I got some more reading material here on that stuff, if you guys are interested. I think this is some of the last intro material that we're going to cover. You're going to hear a lot about genotype, genes, and then phenotype. So what's DNA? DNA stands for deoxyribonucleic acid. You see what I mean about the Scrabble? These are excellent words. Lots of Y's and X's. And then nucleobases, they're building blocks of DNA, so are nucleotides. And then genes are the specific sequence of these things. Right, so you have a specific sequence, and most of them will be, you probably have seen like GA, TC, U, TC, GA, something like that. And that just stands for, those letters stand for various nucleobases that are part of this phosphorus ribonucleotide backbone that essentially makes up DNA. So it's code. But what people don't know is that this genotype, this represents like the exact genetic makeup. All right, I have Alex right here, and his entire genetic makeup from A to Z is all of these letters, and there's like millions and trillions of these things. But what people don't tell you is that genetic makeup, although is set in stone, is not the end-all be-all, because there's something called phenotype, right? And the phenotype is an organism's actual observed properties, often referred to as genetic expression. So something's going to come along. There's an enzyme called polymerase. It's going to come along. It's going to read the DNA, and it's going to make proteins and other small molecules that are going to have all kinds of downstream effects from that, right? Now, if you have a gene, let's say, that makes you more susceptible to heart disease, but it's not being expressed, who cares? So right now we've got this huge push in genomic medicine, and people are trying to identify all these genes. And I think that's great research. It needs to be done. But if you get a certain genetic profile and someone says, hey, you have this gene, and you have HLA-DQ 8 and 2, and that makes you susceptible to celiac disease, well, guess what? If they're not being expressed, they're not a problem. So what changes the expression of genetic material in human beings? Well, it turns out that environmental factors such as nutrition, exercise, stress, sleep, these two are somewhat related, disease and pollution have a substantial influence on your phenotype. So there's some people that'll tell you, I'm fat because, it's part of my genes. There's a possibility that that's the case, but that person has more control over their genetic expression than they think. So, just to get the point across, it may seem obvious to you. So here are two German twins. This is an example that Art Devaney likes to bring up. I've got my own that's following. So these are two German twins, Odo and Ewald. Their genetic material is exactly the same, right? This guy's an endurance athlete, you can tell, right? And this guy's a bodybuilder. So obviously the environment plays a huge role in the outcome. Right? They're not exactly the same, even though they have the same genetic material. This is one of my favorite. The picture's not coming out quite as nicely as I would like it to. These are agouti mice who have the same genetic material. But you notice that the one on the right is a little cuter, it's a little smaller, a little darker. The one on the left's a little fatter, has lighter hair. The only difference between the two is that when the mother was pregnant with this one, they fed it a lot of folic acid. Folic acid is a methyl source, and that methylating agent is going to methylate DNA and change genetic expression. Right? So you now have like a leaner progeny just because the nutrition was different. So what I was saying earlier, you have a client that says, I'm fat and it's in my genes. Well, it turns out that, you are what you eat, but you are also what your parents and your grandparents ate, unfortunately. So if your mom had a really crappy diet, had gestational diabetes and whatnot, you are born with a disadvantage. So there are some people that are somewhat different than others, that might have more difficulty losing weight, that might be more susceptible or more sensitive to sugar and whatnot. And I want to stress that because when the whole epigenetic thing came out, people are like, oh, you see, you have full control of your genes. I'm like, just wait a minute. There is a difference in gene expression here. And it goes through one generation to the other, and there can be an effect, a detrimental effect. I'm not saying it isn't reversible. Most of the time, you can get really good results by changing your nutrition, exercising, and whatnot. Yep.
Does it mean that your lifestyle can be kind of carried on over like other generations?
Yeah.
That used to be really contested by scientists.
No, it's fairly well known. And you look at populations who went through famine, and then you look at their children, and the children. There's two situations. Sometimes the children put on weight really easily, depending on the level of famine. Whereas if they just got enough calories, like the children are really robust. So there's a huge effect, absolutely. And this is transcription. I'm actually not going to go over that, but this is just how genes make proteins and the whole RNA process and whatnot. So the first part of the talk is going to focus on this thing called the metabolic syndrome. Used to be called in 1998 Syndrome X. Some people still call it Syndrome X. So in 1988, Syndrome X was, insulin resistance. And insulin resistance gives you glucose intolerance, hyperinsulinemia, elevated triglycerides, lowered HDL cholesterol, hypertension, and all of these things are risk factors for coronary heart disease. The current definition is a little bit more complicated and has more variables in it. So if your body size index increases, your BMI increases, especially central adiposity, and that is coupled to insulin resistance and hyperinsulinemia, then your glucose metabolism suffers, uric acid metabolism suffers, and then uric acid increases and uric acid clearance decreases. Dyslipidemia occurs, and dyslipidemia means that your lipoprotein profile is getting all screwed up. So triglycerides increases, HDL decreases, and then you get small, dense LDL. Sympathetic, so you get a hemodynamic aspect to it. So your sympathetic nervous system activity increases. Sodium retention increases through the action of aldosterone. You get hypertension. And then you have other risk factors such as C-reactive protein, fibrinogen, and whatnot that come into play. So this is just a multivariate problem, and you probably want to prevent it. It's in your best interest to prevent it. All right. There is over